Hello everyone and welcome to our presentation. I am Vishwadeep Purkastha and we are Group 8 and today we present to you our presentation on demystifying diffusion models, how they work under the hood, how they compare to GANs and why they've become the go-to approach for state-of-the-art AI image generation. So let's go on. So let's start with the introduction. We walk you through the core forward and reverse processes here that power diffusion models. So it starts from inserting the starting image. We begin with a clear, detailed photograph or artwork as the starting image. Then we move on to the forward process, where we gradually add small amounts of Gaussian noise, step by step, until the image is nothing more than a random static. Then, going on to the reverse process, a neural network is trained to invert that corruption at each step so that it removes the noise it just learned to add, slowly unveiling the structure hidden in the static. And finally, after all the iterations, the model produces a completely new high fidelity image guided purely by the patterns it absorbed during training. Now let's see why diffusion models outperform GANs. We'll compare diffusion models to GANs through this. So let's begin with the limitations that GANs have. So GANs pit a generator against a discriminator in a zero-sum game. However, this can lead to unstable dynamics. The issue is that they frequently suffer mode collapse, where only a few styles or subjects ever appear. And they can also produce visible artifacts, unnatural edges, strange textures that give them away. So now that we've understood the limitations of GANs, let's see some advantages that diffusion models offer. So by framing generation as a gradual denoising task, training becomes remarkably stable. There's no adversarial tug of war. The stepwise process encourages diversity. You explore the whole data manifold instead of just a few moves. As a result, the diffusion outputs that appear tend to be much more natural and artifact free, whether you're generating faces, landscapes, or abstract art. Together, these strengths explain why diffusion models have rapidly eclipsed GANs in image generation benchmarks and in the creativity of their outputs.
Now let's dive into the core mathematics that makes diffusion models work. At high level, we train a neural network to undo noise step by step. Then comes the forward process, in which we first inject Gaussian noise into the image in small increments. This is our noise addition step. The forward process is simply known as statistical corruption. We know exactly how much noise we add at each timestamp. New network prediction comes next. Every time step, the network sees the noisy image and predicts a slightly cleaner version. This is the neural prediction. Training aligns the network's output with true noise statistics, which stabilizes learning. Then comes stochasticity for diversity. We then inject a tiny bit of fresh noise back in to preserve randomness and to avoid to a single solution collapse. Then comes reverse sampling. Finally, during inference, we run the reverse chain, repeatedly remove the noise based on the network's predictions over many time steps. A coherent image emerges. This reverse sampling is what lets us go from pure noise to high fidelity creative outputs. Next comes our text to image conditional diffusion magic. For the context, I'm going to say that the text conditioning revolutionized image generation. Can now guide the denoising process with a simple prompt. Then regarding the workflow overview, I'm going to talk about first the text prompt input. User provides a descriptive prompt, and this becomes our conditioning signal. Then comes the noise initialization. We start from random statistic noise, which is the canvas for generation. Then comes guided denoising. At each denoising step, the model incorporates the text embedding to steer the output towards the prompt. Finally, we have our image output, and after all these steps, we get a clear, coherent image. Next comes why diffusion models excel. I'm going to talk about 3 points. The first one is flexible sampling. We can vary the number of denoising steps or swap in deterministic samplers like DDIM to balance speed, quality, and diversity. Then comes guided generation. Techniques such as classifier-free guidance let us amplify or attenuate the conditional signal on the fly, given the fine-grained control over creativity versus faithfulness. Finally, we have stable and creative part, which is the rigorous probabilistic foundation that ensures stable training. While injected noise injects various endless variations, you get reliable high quality images that will still surprise you. And why this matters is because it is a unique blend of mathematical rigor with creative stochasticity. And this is why diffusion models often outperform GANs on image fidelity and diversity benchmarks. Finally, I'm going to talk about how we are balancing creativity and inversion in diffusion models. The first point is the stochastic noise challenges. Adding noise increases sample diversity, but makes exact inversion recovering from a specific image a bit harder. Then comes the deterministic diffusion trade-off. Variants like DDIM replace randomness with a fixed update rule. Inversion becomes straightforward, but you lose some of the model's creative power. Next comes the innovative latent space. Recent research is exploring how deep a meaningful latent representation, even in the presence of stochastic noise, aiming to combine both of the world is. Finally, we are going to talk about the potential benefits. A robust latent allows zero-shot editing, can invert an existing image, tweak the latent, and resample without sacrificing randomness. This opens up the guided image setting and more reliable reconstruction tasks while keeping creative variation intact. In the next section, we'll look at the practical methods for achieving this balance in the state-of-art diffusion frameworks, and Akarshan will be continuing on from that section.
So, hello everyone, myself Akarshan, and as Abhay has already presented about, the latest advancements in the diffusion models, I'm here to talk about the qualitative aspects of this paper that deals with the latent space innovation. Cool. So essentially, the paper tries to delve into four major aspects of the entire system. The first one being latent space innovation. The second one being DPM encoder, which basically allows for the diffusion of an image from a latent noisy sequence. Then we have an application of this DPM encoder and latent space innovation, which is called as cycle diffusion. So this is a new process, or basically a new sort of a model that they have developed that allows us to switch from deterministic modeling of diffusion models to stochastic modeling of diffusion models. This also enables zero-shot editing. And the final application, how they have actually made it into an application, is based on a plug-and-play guidance system. We'll be talking about all of these three or four things in detail later on. Cool. Moving on to the next slide. Let's talk about the latent space definition in diffusion models. So what happens? Consider this scenario. You have two models, model A and model B. Let me actually go ahead and bring to you the entire text that is there on the slide. So consider from model A, you start from an initial image and then you do the forward diffusion process so that you end up with a particular latent. Now that particular latent, let's call that x of t for now. So you started with x of 0 and you ended up at x of t. Uh, what this paper tends to analyze is that what we're trying to do is to model a stochastic, make a deterministic approach towards a stochastic model. How is this possible? Let's have a look at the diagrams. So in deterministic DPMs, you start with a xt and then you go towards an x0 with a linear ordinary differential equation. What happens in stochastic DPMs? We start with an xt, but while during the modeling of this ordinary differential equation, you add random samples from Gaussian noise. So this is what makes the entire process stochastic. You don't know what noise you'll be sampling from the Gaussian distribution. Hence, the clear difference between a deterministic DPM and a stochastic DPM is that you're not able to go on a reverse process from an image into the latent vector. So for a deterministic DPM, you have a fixed way, but for a stochastic DPM, you do not have a fixed way. Here is where our latent space definition comes up. So earlier during the discussion, I told you that we had two models, model A and model B. So we went from x0, which was the initial image, to x of t, which was the latent that we created, using the same forward diffusion process that we as usually do. But in the backward diffusion process, if you call them, let's suppose you model these four processes as F1, B1, F2, B2. So in the B1 process, you'll have to note down each of the noises that you're adding to this latent to convert the xt to x0. Hence, let's suppose if you start from xt, you're going to xt minus 1. So the very first epsilon that you're adding, epsilon of t minus 1, that you'll be noting down and storing in the latent vector z. Then, similarly for epsilon of t minus 2, up till epsilon of 1. So the entire latent vector Z is sort of stored, thus making the entire random noise generation more deterministic and basically applying you to have a reversible process. Now, once you have this latent vector Z, what happens is that you go ahead and sort of map this to the backward process of the model B. So what happens is that now you have this stored. Okay, I have the forward diffusion process, I have the backward diffusion process. In the backward diffusion process, I have stored all the noises. So in the backward diffusion process of the second model, you will go ahead and start picking corresponding epsilon 1, epsilon 2, up till epsilon t of each of these samples from the latent vectors. So this is how we try to convert between a deterministic approach to a stochastic DP. This is what the paper analyzes, and this is what is explained on this slide as well. Cool. So moving on to sort of the application of this. This is the cycle diffusion application. So what that allows us to do, it sort of allows us to go ahead and edit models in latent space. People in the future will also be discussing about how images will be converted from horses to zebras and all that stuff. We'll look into that. So make sure to watch the video carefully. The second part is the decoding, which is basically generating an edited image from a modified latent representation. It also allows a lot of flexibility so that you have, a one shot and zero shot sort of hyper tunable editing method without actually going ahead and, determining every step of the process step by step. The last thing is that this process is very consistent. So the paper ensures through a plug and play system that I'll be going ahead and talking about later that this process is very consistent. So let's talk about the DPM encoder a bit. So the DPM encoder is basically allowing us to make an analytical forward pass, sort of defining the model process as x of t is equal to under root alpha t x of 0 plus under root of 1 minus alpha t into epsilon, where epsilon is sampled from a Gaussian noise. This is basically the forward pass. That is what the DPM encoder allows us to do. But yeah, this is the normal forward pass. But the main source of importance is that this DPM encoder sort of allows us to translate our proceedings into something called as a plug and play guidance system. So you have a source encoding, you have domain translation, you have decoder targeting, and you have zero shot editing. As you can also check in the image that is given above, we have unpaired image to image translation and plug and play guidance as sampled by this paper. The last part, we'll be talking about the plug and play guidance in latent space. So remember I talked about cycle diffusion. So cycle diffusion is enabled because of this plug and play guidance system. So since we had four different processes, F1, B1, F2, B2, each of these are based on a process of energy sampling. The energy sampling process is based on a broader term called Langevin dynamics. The equation for Langevin dynamics is given as follows. This is nothing but a sort of a mixture of both the forward pass and the backward pass in the diffusion process, and hence creates a sort of a unified pipeline. This Langevin guidance sort of allows us to have a creative control, thus enabling a user-directed translation from a particular start of the image to the end of the image. And thus, here we have the end of the qualitative discussion in which we discussed that, okay, how can we translate from a particular image to a latent and from that latent back to the image using a stochastic DPM, but in a deterministic. So now I'll pass on the presentation to my friend Aditya.
Hi, I'm Aditya Rohela, and my friend Akarshan just talked about the qualitative aspects of this paper. Now let's take a look at the deep dive on the quantitative aspects of this paper. We want to see the maths of this paper, right? So let's take an example. So let's say this is a diffusion model that creates horse images. So we can see that you give it a horse image, and in the forward diffusion process, it creates a latent vector. And that latent vector, when you pass it through the backward diffusion process, you get another horse. Let's say this whole diffusion process is a stochastic diffusion process. So every time in F1 and B1, you're not solving an ordinary differential equation. Rather, you are using stochasticity. You're sampling noise from the Gaussian distribution. Cool. Similarly, you have a diffusion model for zebra images. So there's again an F2 and B2, which are again stochastic diffusion models. They are not the deterministic diffusion models. Cool. So now what we want to do is we want to convert a horse image into a zebra image using diffusion model. We were able to do it using cycle GANs, but now we want to see that if we can do it using stochastic diffusion models. So that's why this paper introduces a concept of cycle diffusion. Let's see the maths and the working behind that. So this is a LaTeX explanation of the whole thing that my team made. So let's say originally we had a horse image. Now we send it via the diffusion, the forward diffusion of the horse model, the F1 that I just talked about. Cool. Now let's say there are only three noising aspects, three noising layers in diffusion. So we were able to get the X3, which is the latent space of the diffusion models. Please note that this diffusion model is stochastic. Now, wherever we're going to be talking about, we're going to be talking about the stochastic models only. We're not going to be talking about the deterministic models because this paper introduces the stochastic models and a space for stochastic model, a general space for stochastic models. Cool. Now we have X3 here. Now what we want to do is we want to do denoising. We want to do backward diffusion. Cool. Now we use the same B1 for the horse, and now what we do, we add epsilon 3 to get X2. Then on that we add epsilon 2 to get X1. We add epsilon 1 to get X0. So now what we did was that we took a horse image, we sent it via F1, we got xt. Now we did the backward diffusion to get the epsilon 3, epsilon 2, and epsilon 1 as shown here. So we got x3, epsilon 3, epsilon 2, and epsilon 1. Now we save these noises to make a new latent space. So this z vector is our new latent vector. So how are we gonna use this for cycle diffusion? So we know that in cycle diffusion, diffusion, what we do is we sample epsilon t. In backward diffusion, we sample epsilon t to get a denoising kind of thing. But in cycle diffusion, what they're saying that since you have saved everything in a vector z, you don't have to sample anything. You have everything that you want in the vector z. So what we do is we first take the xt vector and use the epsilon t noise. So what we do is that here we saw that after using via the horse, we were able to create a xt vector. Now let's say this yt is the vector that we here what we do is we create the z vector as explained, the z xt epsilon 3, epsilon 2, and epsilon 1. Now what we do is we pass on that z to b2, which is the zebra model, not the horse model. So we take the x3 and add the epsilon 3 noise to it, or with the sigma t of b2. So the sigma t here will be of b2, the zebra one, whereas the epsilon t will be the noise that we have just saved. So that way we are able to get non-stochasticity in an SDN. Cool. So that's what the slide says, that we generate to generate a zebra from the Z, which is created from a horse. What we do is we use the backward diffusion part of zebra model, and instead of sampling the noise, we use the noise saved here. We can see the noise saved here, epsilon t minus 1 up to epsilon 1. We use this kind of noise. And see, this makes the process deterministic because now in the backward diffusion process, you're not sampling any noise. What you're doing is that instead of taking the xt as a latent vector, what we are saying that we don't care about xt now. I want that you give me xt, epsilon t minus 1 up to epsilon 1. This will be my new vector. This is the new latent vector space I have defined. And according to the paper, they're saying that it is deterministic, and it also seems deterministic because you're not sampling anything, right? Now, this resulted in a general latent space for stochastic diffusion models. So earlier, what you were doing is that you were not able to convert like a horse to a zebra because the latent space will be different for both of these guys, because when you're denoising, for both of the case, it might be different. So now what they do is that denoising aspect is thrown out of the picture. The sampling of the noise in the denoising part is thrown out of the picture because we are saving the noises. That's the crux of this whole paper. Cool. So now let's take a look at the various metrics for image to image translation, the translation from a horse to a zebra. So there are various scores that are provided in the paper. The first of them being the Frechet inception distance, then the second being kernel inception distance, third being peak SNR, the signal to noise ratio, and the fourth one is structural similarity index. Cool. So we can see that for the cycle diffusion, which is the new model, it is showing a better FID, so it is more realistic. Then similarly, KID is shown of 20.30, but it's not specified for the previous model. The peak signal to noise ratio is comparatively worse, but we can see that the structural similarity index is way better than the earlier models. So the authors are arguing that it has been shown that SSIM is much better when we talk about the human visual perception then squared based distances like L2 and PSNR. Cool. So now let's take a look at the photo editing and restoration with zero shot editing. So I would like to hand it over to my friend Unnat.
Hello everyone, this is Unnat Maheshwari and I will be talking about the qualitative discussions of the applications. So beyond the metrics, cycle diffusion unlocks a whole toolkit of real world image tasks, each grounded in paper's core sections. So let's start with first one, which is photo editing and restoration with zero shot editing. So imagine your holidays photo, golden autumn leaves dusted with snow, as you can see on the left of this slide, or a selfie with blemishes you had rather erase. With cycle diffusion's zero shot editing, you simply encode your image, swap in a text prompt like Winter Wonderland and decode. No manual masking is required or no color grading is needed. This exact capability is demonstrated in section 4.1 of the paper, where unpaid translations, example cat to dog, preserve lighting, pose, and background while changing the domains. So let's move on to the second one. Second one is the art and style transfer with diffusion models. Artists can transform a basic sketch into a Monet style or a Van Gogh style is a masterpiece by changing the text condition. No extra style transfer network or paired dataset is needed. So in the section 4.2, the authors show how encoding under one prompt sketch and decoding another like Monet painting yields faithful style swap in true zero shot fashion. Now moving on to the third one, which is the domain adaptation in medical imaging. Suppose you have an MRI image from scanner A, but you need to look them through scanner, like it has come from scanner B for a multi-center study, you can say. Cycle diffusion can translate between scanner domains, preserving exact anatomy with while adjusting scanner special artifacts. This general unpaid translation comes straight from section 4.1 as talked earlier in zero shot learning, proving the method works for any two image domains, including medical scanners. Now, the fourth one, interactive content creation. Game developers and filmmakers often start with rough mockups, a crumbling skyline, a misty forest, a sci-fi corridor. With cycle diffusion, you encode that mockup once, then iteratively tweak your prompts. Make it dark, for example, make it darker, add neon accents, insert alien fauna, etc. etc. And each new version holds your original composition. This rapid prototyping flow leverages the text condition sampling pipeline as described in section 4.2. Now let's move on to the fifth one, plug and play AI assistance. So picture a smart design tool or mobile app. You upload a product photo and type, make it more premium or add glasses, and the system instantly tweaks the image. No retraining, no new data. That's latent guidance in action. The section 3.5 of this research paper lays out energy-based Langevin sampling in latent Z-space, and section 4.3 show how clip-based guidance steers generation on the fly, all within one unified platform, as you can see in the slides as well. Now moving on to the sixth one, fine-grained data augmentation with guided diffusion. So in machine learning, rare class enhancement can starve a model of examples. Think a specific type of tumor subtype in medical imaging. Cycle diffusions, guided diffusion can generate dozens of realistic, diverse examples for these underrepresented categories. Section 4.3 plug and plays guidance experiments on low density prompts demonstrate exactly this use case, giving you high quality synthetic data without any training. You can see on the slides that there is no training required as as it uses diffusion models without requiring new paid data for retraining. Full creative control, user can has full control over its defined images, prompts, encodes and adjusts conditions accordingly, and in a similar way decodes the output. And we have a flexible pipeline which supports research, industry, and creative applications with adaptable workflows. So what ties it all together in a single consistent workflow? So first is zero shot learning, no paired images or fine tuning. Second is perfect reconstruction. BPM encoder recovers the exact latent to rebuild any real image. Third, one unified pipeline, editing, translation, and guidance from photos to medical scans are all powered by the same stochastic latent framework. This combination of simplicity, fidelity, and flexibility makes cycle diffusion a true Swiss Army knife for image manipulation. For hobbyist approach apps, photo apps, and interactive design tools to critical medical images, this is this can be widely used.
Hi, my name is Dhruv and I will be talking about qualitative discussion of cycle diffusion. So the first is encoding process. Let the original image denoted with x0 belongs to RHWC, where HWC are the dimension of the image. In a diffusion model, forward missing is governed by a predefined noise schedule at each time steps 1 to 2t. Noise is added x0 according to q of xt with respect to xt minus 1, that is previous image. This process accumulated into a single step formulation q of xt with respect to x0, where n is equal to xt under root alpha t bar x0 comma 1 minus alpha t bar I. Truncated forward sampling is to choose a truncated time step TES less than t. Example, TES equal to 200 for t equal to 1000. Sample a noise image time step TES. XTS belongs to Q of XTS with respect to X0. Now compute the noise estimates epsilon naught t that would reverse the steps from XTS to X0, that is initial, using a trained unit denoising model epsilon naught 0. The sequence of this predicted noise value implicit capture the truncated latent. This latent embeds the structural and content specific information of the source image but stops short of complete destruction, full noise. Second is decoding process, conditional reverse denoising. Now to perform editing, we decode the latent Z, but this time condition denoising process on a different prompt, ETGL, a man wearing a crown. Example, we reuse the same noisy image XTS but change the guidance xt minus 1 is equal to d of xt comma t comma epsilon naught tgt for t equal to t epsilon naught tes minus 1 to the 1 using the same denoising unit mode. The process reuses the same latent noise but change the guidance, allowing the model to reinterpret the latent features under new semantic while retaining the source structure. So the third is the trade-off. So it has low TS and high TS. Low TS, more semantic freedom, example completing change here, clothes, objects, risk of losing structural fidelity. High TS, more structural preserved, example lightning, face shape and layout. Edits are more subtle and custom. So the next is cross attention map control. Diffusion model with the text conditioning typically uses cross attention layers to align images tokens with text tokens. Cycle diffusion can freeze or blend with the attention maps to enforce stronger spatial alignment. Techniques: attention freezing, attention blending. This preserves fine details like facial features, object shapes, background structures, while editing localized attributes. Next is SDET cleanup. After decoding, a short post-processing step improve visual quality. Inject a small amount of noise, x1 bar equal to under root of alpha 1 bar x0 plus under root 1 minus alpha 1 bar epsilon equation of noise. Run denoising steps against. This technique is borrowed from SDET, visual artifacts over smoothing, texture inconsistency. It helps to reduce these kind of things. So the question arises, why is it smooth and stable? Even after dramatic changes, cycle diffusion keeps the latent noise seed the same. So scene layout, lighting, and identity remain recognizable. Edits feel natural and coherent, not like a completely new image. Contrast with naive prompt to prompt editing, where structure often get lost. Cycle consistency checks to validate how much of original image remains. Cycles the editing image back through the same pipeline but in a reverse. Encode X edited with epsilon TGT, decode with epsilon source. If reconstructed image is close to original x0, then cycle error is x0 minus x0 bar, that is tends to 0 if it is close. So the example glass to crown, your selfie with caption a man wearing glasses, truncation TES equal to 300, target prompt a man wearing a crown. Results what stays, face shape, pose, lightning, camera angle, what changes, glasses are replaced by clown. This works because the image was regenerated from scratch. It was gently redirected in a latent space. So, thank you.